take you from like v to v prime if the size of v is n. No, I think there's a lot more than 5 possible. Oh, he's being funny boy. Yeah, right? Take any vertex of G, and if I'm imagining all possible bijections between these vertices and these vertices, then I have 5 choices for what to match it to. Agree? Say agree.
Agree.
And then go to my next vertex in V. Then I have again 5 choices for what to match it to, etc., etc. So I claim, and he does too, is that there are in fact that the size of the set of all of these functions is in fact n factorial. In other words, the number of one-to-one, the number of bijections from a vertex set to another vertex set grows like factorially with the number of vertices. So like the robots are kind of screwed too a little bit, unless they're, but still 20. I feel like they could just do it, and we just couldn't. Yo, there is a website that trains you. I'll send it around. Okay, good. Next, we're gonna do the whole next section. Ready? What? Sure. That's true. You could find the one that. Yeah.
Yes, and then
all right, good.
Permute the ones that.
No, the nerd life is the good thing.
All right, next. One of the biggest concepts in graph theory is that of planarity.
I swear to God, we're not talking English anymore.
So, okay, good. What does it mean for a graph to be planar? Should I start with like the famous problem? Let's start with the famous problem. There is a famous problem. It is called the 3 houses, 3 utilities problem, or something like that. This is famous.
Yeah, it's the one on the coffee mug. Yeah.
It's the thing on the coffee mug. Yeah, did you watch this video went around a couple years ago? Okay, good. All right, so who would like to participate in the story? Woo!
Shreya would also like to participate in the story.
Okay, good. So, good. So we have 3 houses. It got bigger for some reason as I went
Some of
on.
us are richer than others.
I'm that one.
Okay, this
Nope.
is Shreya's house.
Wow.
This is Sophia's house.
Oh, the middle-sized house.
And who's the other person?
Who wants to? Anyone else? Evan? Evan, you want the big house?
Big houses are stupid. I'm stupid out there.
Yeah. Oh, imagine what the big house.
Very good. Alright, and now we have good. Now we have 3 resources. What are the things that everyone needs to survive? Like water, electricity, Wi-Fi, what else?
Candy. Food.
Candy.
I like Wi-Fi.
Okay, good. So let this be water.
Bacon.
Good. So here's the water supply. Here is bacon. And here is like love. Wait, this just got weird. All right, good. So, good. And so this is typically done with good. This is typically done with like water, electricity, and say, gas or something like that, right? Okay, so these are sort of, you should think of these as resources which are being supplied from some central sort of authority in the town or something like that, and they need to go to the houses. All right, so we need to build these pipes kind of underneath the ground, but we do not want the pipes to cross, because if the pipes cross, that's bad. Okay, so how might we do this? Well, what's most important? Maybe water. So perhaps I will just send a water pipe from the water supply to Shreya's house, and then to Sophia's house, and then to Emmanuel's house. Is that an E or A?
That's an E.
Okay, good. Great. That seems to be no problem. Well now, let's send bacon. What? That was a stupid idea. Good. So how can we send bacon to all 3 houses? Well, I cannot send bacon to Shreya's house like this because, like, you know, right? But seemingly I can go around. And I don't know if you have any thoughts about the best way to do this. So, okay, Shreya now has bacon. Can we get bacon to Sophia?
Yeah.
Seemingly we can, right? Which way do you want to go? I guess we have to go around, right?
I have no idea what you're saying.
Okay, can we get bacon to Emmanuel?
Yeah.
All right, now we have 2 choices of how to do this. We can send bacon to Emmanuel like around back within the bacon way.
But it doesn't matter.
Well, you say it doesn't matter. Well, okay, let's just try that, and then I'll. Well, no, let's see. Should we do this now?
We want to send it around back.
Yeah. I mean,
Well,
it doesn't matter.
Either way, we're kind of screwed, right? In fact, we can talk this out right now, right? If we send bacon to Emmanuel's house this way,
Shut out.
now what's wrong?
Sophia
There's a
won't get any
monopoly of love.
Sophia
Now
won't get any
Sophia is not going to get any
At
love.
least she has bacon.
I'm a vegetarian.
Oh my god. So yeah, so good. So there, can we get even love to Shreya?
Yeah,
Yeah.
Yeah, we can. Yeah, we can get love to Shreya like this, right? Sha. And we can get love to Emmanuel, but to Emmanuel's house. But but does everyone see that Sophia's house is like trapped, sort of in between? Yeah.
Yeah.
Okay, good. Whew. And so might we have tried this differently? Well, we could have instead sent the bacon.
Oh, the other.
Yeah, we could have gone the other way around. That. Hold on. So if we do this
Oh, wait.
to Emmanuel, right? But now again,
Sophia's still
again, we can't get love to Sophia anymore, right? Because Emmanuel's bacon pipe has gotten in the way. Good, that was a real sentence. Never been uttered before in the history of humanity. All right, good. Good. Okay, some philosophical points now. Okay, and so seemingly this cannot be done, yeah? Okay, notice that even though 5 minutes ago I just said, dude, man, the way you draw the graphs is not what's important. What's important is like the graph itself. I said that basically, right? Okay, so now we have to accept the fact that this property of planarity is, what does it mean for a graph to be planar? I suppose I should say that. A graph is planar if, well, if you can draw it without the edges crossing each other. So we are in now some weird place which is at the intersection of like graph theory and like very, very low level geometry. And so low level that we're not going to go all the way there, man, because we're not going to go there. But notice that the same graph can exist in a planar version and a non-planar version. Take this graph I was just mentioning on the back board. Here's the graph, yeah. Let this be V1, V2, V3, V4. Or rather, I should say, this is a picture of a graph or something like that. But the same graph could be drawn differently. And let's see, V2, V1, V4, V3. And now notice V3 and V4 are connected, V2 and V1 are connected. Good. And V1 is connected to V4, and V2 is connected to V3. So notice what's going on here is that this is the same graph, like the legit actual same graph, but drawn in 2 different ways. So the vocabulary for this is that this is called an embedding. An embedding is a geometric manifestation, a like realization using like the points and lines of like geometry of the edge-vertex relationships in a graph. This is one embedding, this is another embedding. This embedding is planar because it can be drawn without the edges crossing. This embedding is non-planar because in this case the edges cross. Follow? And therefore, what we say that a graph is planar if there exists a planar embedding. Is everyone okay on the vocabulary? Okay, good. All right. So when we say that a graph is planar, we mean that there exists a way of drawing it such that the lines do not cross. And then when we say a graph is non-planar, we're making a claim about every single conceivable way that you might draw those points and lines crossing on a flat two-dimensional plane. That's built into the concept. Okay, so there's a million questions that you might have now about geometry issues. So maybe we'll just let them come up organically. All right, good. There are two big theorems, three big theorems about, two mini theorems and one big theorem about planarity. Ready? One, K5 is not planar. That is very reasonable if you spend about 1 freaking minute trying to draw K5. And if you spend any time trying to draw K5, I mean, already, well, I guess I can do a couple more. And now it's just like,
No, go around the outside.
oh, I could go around the outside, he says.
One in the middle. Keep one through the center.
Okay. So maybe he's right. Maybe it's like just barely not planar. Let's see. I
you
can
do one through the
do.
middle.
No, I'm just already screwed,
Well, you
right?
can do one more through the middle, but then you're out.
Yeah.
Sure, but I've already determined that this vertex
Now it's cut off.
is cut off from this one, right? Even before I drew this line, right? This vertex is cut off from this
You
one.
do need that line, so otherwise you can just go to that.
No, I can't get from here to here.
Yeah, you can.
Oh, It is now that these two vertices are covered.
Can't you just like,
What's up?
oh, but then you,
Yeah, and so conversely, if I tried to go, what was I going from here to here? No, from here to, what the hell did I do?
if you go like,
Whatever, it can't be done. I'm not going to prove this right now.
yeah, I can.
I got another proof for you that K33 is non-planar. All right, and then comes the big theorem. And the big theorem is called Kuratowski's theorem, which we're also not going to prove, though proofs are available. What someone's giggling. Kuratowski's theorem says, I've never had anyone like enjoy this class so much. What are you googling?
She was like, no, they wrote bacon.
Bacon pipe, not bacon
I
poke.
know, I
Yeah,
autocorrect.
Yeah, the students are going crazy. Good. All right.
Okay.
Let the record show that people are just googling bacon poke and giggling. That's what's happening in this class. Good. All right. Anyway, back to. Can we go back to this?
Yeah.
Lemma 1, K5 is non-planar. Proof. Next class. Lemma 2, K3 is non-planar. Proof coming in 1 minute. Theorem, big theorem, is that every non-planar graph, I'm going to be intentionally vague about this at the moment, kind of just like has inside of it a K33 or a K5. In other words, a K5 or K33 type arrangement exists as a subgraph of any non-planar graph. And you could almost say it is like because K5 and K33 are non-planar, that a graph is non-planar. Yes?
Are they like the smallest non-planar graphs? Is that why?
They are something probably like, they probably are the small, yeah, that's probably just true, right? I bet you can prove that every set of 4 vertices is planar. That seems just like true, right? Because K4 is just planar. That's a really good question. Yeah, let's just take a second to do this, right? K4 is just planar. Am I saying that right? I believe it is. Yeah, because watch. Okay, check, say check.
Check.
Good. So if K4 is planar, that's interesting. So now
Like 5 vertices, 4.
so you need 5 vertices at least for a graph to be non-planar. And note that K5 with even 1 edge removed is planar. Agree? So of course I haven't proved yet that K5 is non-planar, but once I do that, then we can say that K5 is in fact the smallest possible non-planar graph, judged by the number of vertices. And then, I don't have a further comment about K3. Okay, good. Does everyone see that this just is K33, right? The water, bacon, love, Shreya, Sophia, Emmanuel graph is the K33 graph. Okay, let us prove right now that K33 is non-planar. All right, what's up?
Is
K32, that's a good question. I don't know. I bet it just like is, right? Because like cha.
Yeah.
So didn't I just do that?
Yeah.
Does Gus do Kurt Gus do?
He does not prove it, no. Proofs exist. There are, I considered doing it one year. This is not the year that's going to happen. It can be done, it's like 20% harder than the next hardest thing we've done, but not like 100% harder. Like it's doable, it's very long. Proofs exist. Okay. Whew. I think if you ever took like an entire class on graph theory, then you would do it. It's one of these core theorems. Okay, good. Wait, we got what? 6 minutes? Let's go. K33 is non-planar. Okay, this is oh my god, so much giggling. Good. This is hard because we need to quantify over all possible embeddings. Does everyone see this? If we're going to do a proof that's like legit, well, we need to draw things in every single possible way that they can be drawn. Okay, and doing this rigorously is like borderline not possible. So all right, let's go. Well, thankfully I have been encouraged to show that K4 just is, oh no, okay, let's not start with that. Let's take, so here's what we have. We have, how does he do it? He says, yo, take K33 and let the vertices of K33 be A, B, C, D, E, F. In the standard way, such that A, B, and C are members of one of the sets of the bipartition, and D, E, and F are on the other. So let's let these be a member of, say, alpha, and these be members of beta, or whatever. Okay, what I want to do is show that no matter how hard you try, this is simply not possible. Okay, so what we need to do is, my claim now is, because this graph is completely symmetric, without loss of generality, select any select 2 vertices from alpha and 2 vertices from beta. Okay, without loss of generality, let them be A, B, and D, F, or D, E. Okay, how can we draw these? Well, the sort of dumb way to draw them would be to draw, to do it like this, right? Because this is sort of already not planar. Okay, but is there a sort of good way to draw these? Yeah, there is, right? With them with it flipped. Okay, so I claim that this is the most difficult sort of part of the proof, is this sort of first step that says that the only possible way to arrange 4 vertices of K33, 2 from one set of the bipartition and 2 from the other, is like this. And we put A and B are members of one set, and D and E the others. The problem is that once we put them, I'm coloring for what set of the bipartition they're in. Once we connect A to E and D and B to E and D in the only possible way that we can, such that they're such that the edges are not crossing, then we have created this region. And now, where do we put, say, C? Well, there are 2 options of where C can go. C can go, so here's A, E, D, B. I'm going to just rush this in the last minute. So case 1 is that, let me just finish drawing. Case 1 is that we put C inside this region, R1. What's wrong with that?
Can I
Oh, that's case 1, and I'll draw case 2. What's case 2? Is that C is outside this region. So let's call the inside R1 and the outside R2, inside R1, outside R2. Well, case 1, that just has to be that C is either inside or outside, right? Okay. Well now, case 1 divides up into 2 further subcases, because where do we put F? Well, if we put F inside, we're screwed, because, wait, let's see, C was a part of the blue, right? And F was a part of the red. Why are we screwed with F on the inside?
You already sliced it in half with
Yeah,
AC.
because putting C here means that now C has to be connected to E and D. But however we connect C to E and D, we further subdivide region 1 into 2 subregions. And F must land in one of those 2 subregions. And whichever subregion F lands in, it can connect to the only other blue one that it needs to, and it can connect to C, but F simply cannot connect to A. And if F happened to land in the other region, same thing. And then the other option is if C is on the outside, but if C is on the outside, then where do we put, oh, and I guess I needed the case where F was on the outside too.
Then I can't get to see.
F can't connect.
Yeah. Okay, we can go over these cases a little bit maybe more carefully, because there really are like sort of 4 subcases per case. It just takes a couple minutes. Good. Who is going to be here on Wednesday? Is it like no juniors or like some not juniors?
Wait, some that's
Okay, it's going to be polyhedron day. It's going to be really awesome. Good, come back to school.